So on this next problem, we've got a piece of copper and we're heating it for 2 seconds, which doesn't have anything to do with it. 100 joules of energy are transferred to the copper. And you can tell that the copper is getting it because it went from 20 Celsius up to 71.9 Celsius. You can use this information to calculate the specific heat of the copper. Now, Q equals mc delta T, and C is the specific heat. So if you solve for it, then C is going to equal Q divided by M times delta T. So see if you can figure out what the value of C is. C values are always positive. That last value doesn't make any sense because negative ones are kind of science fiction. And delta T can be Celsius or Kelvin. So see if you can figure it out.
Kind of like an unrelated question, is the heat capacity by metals, like do metals have a lower heat capacity and that's why they heat up faster?
Definitely.
If that question makes sense.
Yes, 100%. So metals have a low heat capacity. It doesn't take a lot of joules to make them raise by 1 Celsius. So yeah, so the same amount of heat to a metal will make it go crazy, but water won't go up. So, I used to live in New Hampshire, and the winters were just brutal. But my colleagues to the northwest lived on Burlington, Vermont. There was a big lake, Lake Superior, and that lake absorbed energy. Now, it took a long time to absorb energy, but then in the winter, they would usually be more mellow up there because the lake released its heat slowly and made it a little bit warmer. Yeah, no, that was a really cool question. Very, very relevant. So, yeah. All right, well done. Both of you rock. You're both using iClicker, so it's easy for me to see. Q equals mc delta T. Yep. Q is 100, M is 5, delta T, Celsius or Kelvin. I would just use Celsius. I am the lazy chemist. Make sure that you've put this part in parentheses. Should be pretty chilled. Questions?
So like the 2 seconds is like pretty much irrelevant, right?
Exactly, that's right. At the end of Chem 222, we'll talk about, that's the wrong problem, sorry. We'll talk about time, where the seconds could be relevant, Trinity, but for right now, we haven't done anything with time, So this was just a pretty hot thing, because you got 100 joules in 2 seconds and stuff, but it doesn't do anything. Good. Other questions? Cool. This question is kind of like what we talked about earlier, where you have a hot and a cold, and hot plus cold always equals 0 in thermodynamics. So in this question, we've got 2 samples of water. One of them is cold, One of them, we don't know what the temperature is, but when they're mixed together, the final temperature, 47.9. Now, notice that 47.9 was larger than 22.5, so that implies that the other water sample is the hot one. It'll have a temperature higher than 47.9. So see if you can use this information to calculate the initial temperature of the other sample. So MC delta T of the cold water plus MC delta T of the hot water equals 0. Yeah.
Wait, it has to equal 0? Why does it have to equal 0?
Cool. So all the energy of any system, you never lose or make any.
Yeah.
It's always equal to 0 is what that means. All right.
Okay.
So you could have like MC delta T hot equals minus MC delta T cold.
My question was, could I just set because it's just asking about the temperature, it's not asking about is it asking about the energies or asking about the temperature specifically?
Yeah, I want you to tell me what temperature of the other sample is needed to combine with this sample and make a final temperature of 47.9.
So could we just set it up and it's 47.9 equals 22.5 plus or minus X?
Remember
And
that
I have to use that.
you're close. It's MC delta T hot plus MC delta T cold
Okay.
equals 0. Okay? So it is about the temperature. You honestly don't need the heat capacity, but there's also the N part in there too, Katie.
Yeah.
So see if you can wrangle this out and make it work. We'll talk about it here in a little bit. So good.
Wait, can you just subtract it? Can you just, or add it, the final temperature, because it's both water. So
That's kind of what I'm wondering.
All right. So here's how to knock all these out. All right. We want to solve delta T will be final minus initial hot. And delta T over here will be final minus initial cold. All right. And at the end of the day, all right, you can predict if you want hot or cold. So you've got 22.5, one of the initial temperatures. Your final temperature was 47.9. So the hot temperature will be a number larger than 47.9. Is that part cool?
Yes.
Awesome. So we want to solve for the initial temperature that's hot. So what you want to do is, subtract one side from the other. So let's subtract the cold side. Well, if you subtract it, then it goes over here, minus MC delta T cold equals MC delta T hot. Now, you can divide both sides by the 4.184 heat capacity, so that's out of here. And when you break this part down then, you've got minus the mass of the cold, which was 108, times delta T for the cold, final temperature, 47.9 minus initial, 22.5. That equals the mass of the hot, 65.1, times delta T hot, ends at 47.9, but we don't know what the initial temperature is. So you want to solve for that initial temperature of the hot part. So what I would do is solve for all of this part first, and then we'll go from there.
Yeah.
Yeah, cool. These are great questions. So we have this equation where the mass of the cold times its delta T with a negative sign in front equals the mass of the hot times its delta T. We want to solve for this final temperature. So to do the math here, first of all, divide both sides by 65.1. So that's out of here. So when my calculator just now, I went minus 108 times 47.9 minus 22.5, and then I divided by 65.1, and I got this number, minus 42.138. Now, minus 42.138 equals 47.9 minus x. So to figure out what this is, we're going to add x to both sides. So it's not negative, it'll be positive on this side. And to get rid of this number, we'll add 42.138 to both sides. So 42.138 plus 47.9, I ended up with an answer of 90.1. The answer here says 90.0. I must have rounded a little differently, stuff like that. But that's how you find out this final answer. And the important part here is that if you have a final temperature that's here and you have one temperature which is lower, you must have a temperature which is higher, all right? It has to be closer to a warmer temperature. It can't be 274 Celsius because water boils at 100 Celsius. It would be gas at this point, and that doesn't work. It also can't be this number because it can't be lower than the cold temperature value either. Go ahead.
I went about it a different way, and I was really close.
Cool.
Until the end. How I did it is I had everything set to 0 like we had originally, and then just plugged in what I knew and then solved.
Good.
For everything else. But here, here's where it got kind of sticky.
Yeah.
As I ended up with, once everything moved over sides and canceled everything out, I ended up with 42.1638 equals 47.9 minus x.
Yeah.
And so then
Well done.
I took away the 47.9 and put that on the other side, and I ended up with negative 5.76, but my x was also negative, so it just made my x is 5.76. So
Okay,
I would.
let me stop you there. So you have 47.9 minus x equals minus 42.1.
No, my 42.1 was positive.
Okay. The MC delta T part when you put the water on the other side, there's a negative sign right there.
I think that was my problem, is I didn't move it to the other side. What I did
You can tell
was,
this stuff.
yeah, and I just put all my constants in and everything, and so I ended up with 272.38 times for my delta T, which I don't know, minus 11,000. And then once I divided by 11,000, or I moved 11,000 to the other side, so I ended up with positive 11,000. Then I divided that by 200, and that's how I got the positive 42.
Okay.
So I just I have the same numbers, but I'm wondering what the mistake was.
So if you have a positive 42.1 here, then this negative would have to be on this side. So somehow you're going to have the 42.1 and you'll add it to 47.9.
Okay.
So I think, just make sure you add that negative in there somewhere and stuff like that. But let's say, Caitlin, that you got, what was your answer again?
5.76.
5.7. Looking at the problem itself.
I know it's not right.
Yeah. So that'll give you a hint and stuff like that. So you were really close and stuff. And that's why sticking around on our Friday in a boring chemistry lab lecture is super cool of you all, because it's giving you more experience and stuff. And if you did a problem like this, you'll be much better able to take it on and stuff like that. So my hat's off to you. You've got the skills to do this and stuff. So you too. Questions on any questions, other questions on this one? So
I got a completely different number.
okay, what number did you get?
I got what was it? 27.
27. All right. Yeah.
I think it's just because I did I think my expectations too off, and then yeah, and I'm also tired, so.
This is definitely a problem, the kind of things that you've done in the past, but it's a different application for what we've done. So in both of your cases, like what I would do, like take a picture with your phones of this problem, man, or look at it and just try it later, all right? And go through it and stuff and see at the end if you can get a number like this and stuff, because you're both on the cusp of it, man, and we just gotta get you over that little ledge and stuff, and then you've got it.
So the best way to go about this would be setting my Q hot to negative Q cold instead of like solving for everything and moving it over.
Totally. You could also do it like I started up here, like hot plus cold equals 0. That would be.
That's not how I had it.
Yeah.
But I just don't know like
Oh, yeah.
where it went wrong.
When you do it this way, sometimes people forget to move a negative like one side or the other. All right. And that's why I kind of like this way better, but honestly, they're both fine. And mathematically.
Oh, I figured it out. I had my my second half of the equation was like I was taking it away. Like I was doing okay.
No worries. That's okay.
This makes a lot more sense now. As to why I'm like, but that wouldn't be a negative on the other side.
Yeah.
Adding it. Okay. This makes so much more sense.
Again, my hat's off to both of you just for being here. And that's why it's cool to be here, because yeah, you can check these things out. And it's the more you do these things, the easier they get, the faster you get at them, all these kind of things. So this is an excellent conversation we're all having. So, all right. Other questions?
How many more questions?
Yeah. So I'm on number 14. 15, 16, 17. There's 5 more. Do you just want to talk about them, not like try them?
Either or.
It doesn't matter.
It doesn't matter.
Okay.
I like talking about them.
Okay.
So
I'll just do that. But if you want, I can stop. We can try it and then answer it too if you want. So it's up to you. This is a problem where it wants you to find the enthalpy, and this one isn't as bad as you might think. This type of delta H is delta H per reaction. So what it means is that when you burn 1 mole of C3H8, you're going to get this many kilojoules out, all right? And the question comes down to, well, we're not burning 1 mole, we're burning 3 moles, all right? Well, if it's this much per mole and you have 3 moles, you would take this number, multiply it by 3, you would have 3 times the energy. So 2044 times 3 would give you this number. You're just going to end up with more energy because you have 3 times the amount that the reaction was set for. If this would have been half of a mole of propane, this number times 1/2 would have been the energy. Is that cool? This is a delta H products minus delta H reactants question. And in this problem, these are your products, these are your reactants. Now you will always get values like this for these problems. This is what Leanna was asking about earlier when we did the seminar self-quiz. So to solve for one of these numbers, you would take the products, so the delta H of SiO2 and 2 times the water, 2 times this value, and you would subtract from it the reactants. So you'd subtract 34.3. Notice there's no O2. The elements in their standard states are equal to 0 in these kind of problems. So that's what Leanna was asking about. There's 2 types of these delta H things. This is the other type. You will always get these values. If you don't see something like oxygen, it's because it probably is equal to 0. So here, SiO2 plus 2 times water minus the SiH4 and oxygen 0. Watch the signs of the reactants part. It's easy to forget that part, but it comes out then to be minus 1428.8 kilojoules. You never have to know these numbers, but if I don't give you a number, it's probably because it's 0. Any questions?
So we're just like adding them. We're
It's
adding the reactants in the product.
Yeah, you're taking all of the products and you add the products together and subtract from it, adding up the reactants.
Okay.
Yeah,
And then like O2 was just like.
that's right.
Why is that?
So, like if I had chlorine and I didn't give you the delta H of chlorine, I'm not being fascist or spacey. It just means that that's an element in its standard state and it's going to be 0. Cool. Watch the reactants. A lot of times people will forget about that negative sign. So like they'll add 34.3, but you subtract all of the reactants. That's the one caveat that I would give you. Cool. A molar enthalpy of formation is delta HF, all right? And those have they're special kinds of delta HF. But the punchline for a formation equation, 1 mole of product and all reactants are elements on the periodic table in their standard states. So when you look at these 4 equations right here, this is a compound. It's a mixture of elements. That's not a delta HF. CO, compound, carbon and oxygen, not delta HF. Water, compound, not delta HF. But this one right here, 1 mole of product, so there's only 1 right there, and everything on the reactant side are elements. Carbon would be graphite, hydrogen's a gas, oxygen. I have to use fractions here. I don't like to, but I have to in these kind. So B here is a heat of formation reaction. The other ones would be regular delta H of reactions. And all of those values, like the ones we used in the last problem, those are all heats of formation, how much it takes to make 1 mole of product. So 1 mole of product, all the reactants are elements in their standard states. Look for the compounds, that would disqualify them. Look for 2 or 3 or 4 moles of product, that would also disqualify them. Only 1 mole, all reactants, elements in their standard states.
So we don't want to do any math, it's just identifying.
Yeah.
compounds.
That's right. Like these numbers right here, these are all delta HFs. So making 1 mole of SiH4 from silicon, metal, and 2 H2 gas, that's how they got those numbers, all right? So it's important to know like where these numbers come from, and that's what these heats of formation are all about. It's always 1 mole of product, reactants or elements in their standard states. So that big table at the end of problem set 3, those are all delta HFs. This is what they do. 1 mole of product, reactants, elements in their standard states.
So what's delta HF mean again? Because like delta H is enthalpy.
That's right. Delta H is enthalpy, and there's many different kinds of enthalpy, Trinity. So these other ones, not B, but A, C, and D, I would call those delta H's of reactions, and that's the normal kind, all right? So when you burn gasoline, that's probably going to be a delta H reaction or something. So these formations are like special delta H's, and that's what that table is all about. And you can use those tables to go the products minus reactants. So if you want to know the energy to burn your gasoline, that's what you would use. But you have to know where the formation values come from. As long as you know 1 mole of product, reactants in their standard states, that's the important part. So most of our delta H's are just general delta H of reactions. But these formation ones, which are all those in the table, you can use those then to go delta H products minus delta H reactants. So these are like specialized delta H's. Good. It's forming the compound from the elements, and so that's like a ruler that's used when calculating energy changes. Cool. Any questions? Is that cool? All right. This is kind of a weird combination of delta H reactions and Hess's law. But what you want to do is you want to solve for making 1 mole of FeCl2. We want to find that delta HF for FeCl2. So let me do this while I'm a little bit on the board here. You want the FeCl2 delta HF. And again, if it's got this formation, that means 1 mole of product, so you have to have a 1 right there. And then the reactant will be the elements in their standard states. So you want to have the delta H for Fe plus Cl2 making FeCl2. And you're given all of this stuff up here. And notice that FeCl2 only appears right here. It's a reactant, but we want to have it as a product. Iron only appears right here, and we want it as a reactant. So this is an example of how you can use Hess's law. We're going to flip this equation around so that FeCl2 becomes a product, but we're going to leave this reaction right here. So what I would do on this problem, I would first flip the first equation. FeCl3 is going to be the reactant. It takes 1/2 Cl2 and FeCl2. And when you flip it, you change the sign. Positive 57.7 kilojoules. I'm going to leave this reaction as is. Fe plus 3/2 Cl2 makes FeCl3, and I'm not changing that at all. Questions what I've done so far? Awesome. So now, usually, if you look at those key things like the iron and the FeCl2, often that's enough to knock these out, but let's double check. When you add these, FeCl3 is a reactant, FeCl3 is a product, out of here. 3/2 minus 1/2 will give us our 1Cl2. So that's out of here, and we have just 1Cl2. So when it comes down to it, Fe plus Cl2 goes to FeCl2, and that's what we wanted. So the answer here then would be positive 57.7 minus 399.5, whatever that is. Apparently it's 341.8. Here's the kind of steps involved. So we flipped the first reaction around, left the second one as is, then added them together. So heats of formation again, like we talked about, 1 mole of product, reactants on the standard states. This is the desired reaction, and we want the delta H for it. So flipping that first one, leaving the other one as is, everything else cancels out. The delta H will be the value given. Any questions?
Well, didn't you say earlier that like the final result or whatever would be also provided or something?
So this is one where you have to know about the heat of formation to get to that part. You're right. So we're taking it up a notch a little bit. You're right. In this case, especially after we just talked about the heats of formation, you can see they're kind of important to know. So if maybe by Tuesday, just make sure you know that heats of formation, 1 mole of product, reactants in their element states. Sometimes I cough when I'm saying things that might have other implications besides me just having a cold, which I don't have a cold, by the way. Anyway, so I'm trying to give you a hint. All right. Yeah. Good. Other questions? Okay. This last one is one of those bond enthalpy problems. Bonds broken minus bonds formed. So N2, there's only one N2. You're going to need 1/2 of that. 3/2 of F2, which is this one, 3/2 of that. So the bonds broken minus the bonds formed. You can probably see there's not 1, not 2, but 3 NF bonds. So bonds broken minus bonds formed, 1/2 of the N2 plus 3/2 times FF minus bonds formed minus the bonds of product, 3 NFs minus 105 kilojoules. Okay. Questions?